Everyone. So this unit is called Solutions, and it's going to be really important not only for our understanding of chemistry and just really how things work, but also because it's two gateway topics, okay? And the gateway is coming up in March, so we want to be ready for that. So let's go ahead and get going. So when we started the school last semester, we talked about classifying matter. And matter is anything that has mass and volume. Basically, it takes up space. And matter can be split into these two main categories, pure substances and mixtures. And in pure substances, you have compounds, things that are made up of multiple elements. So baking soda is NaHCO3 or salt, NaCl, multiple compounds. Whereas elements are just like oxygen, gold, iron, just single elements, okay? And these compounds are elements that are chemically combined. And then we have mixtures, which is where we're really going to be kind of focusing in on. And mixtures, there are two types. We got heterogeneous and homogeneous mixtures. And hetero, that prefix there, means different. Okay? And the prefix homo means same. And we're going to use that to help us with our definitions. So mixtures are composed of two or more substances. Okay, you can't have a mixture if you don't have at least two different things, that can be separated by physical means. Okay, and this is important because it's like a salad, right? Like you can pick out tomatoes from a salad if you don't like a salad or if you don't like tomatoes. But if something is like chemically bonded together, you can't really separate that without a chemical reaction. And again, we have our two types. We've got heterogeneous and homogeneous. Hetero meaning different, homo meaning same. And what that means is not that the things that are being mixed are the same or different, but it's how they look. So heterogeneous mixtures look different, and homogeneous mixtures look the same. Okay, and that's where we're really going to see that. So heterogeneous mixtures are two or more substances that are physically combined and they're not uniform throughout. For example, in this granite you can see these little black pieces, the white pieces, the gray pieces, all different colors. And in the Chex Mix you see these Ritz crackers, these little pieces here, this pretzel, okay? They all look very different. Other examples would be any kind of salad or pepperoni pizza. Basically anything that you can see the individual components, or there's a clear difference there. Now, there are two specific types of heterogeneous mixtures. We have a suspension, which is a mixture that contains particles, and they're small particles, that settle out if left undisturbed, kind of like dirt water. So dirt water would, if you have just a cup of dirty water, eventually all the dirt would settle to the bottom. And a type of suspension is thixotropic, which my pronunciation of that may or may not be correct. But basically it behaves like a liquid and a solid. So, for example, toothpaste here. Toothpaste, when it comes out of the tube, flows like a liquid, okay? But when it's sitting on your brush, it acts like a solid. Okay, so that's a type of suspension. And the second type of heterogeneous mixture is a colloid. And colloids have particles that are smaller than a suspension. And so you kind of have like suspension is bigger than a colloid particle, which is bigger than like an atom. Okay, so just to get an idea of the scale. And so an example would be milk. Your milk has these tiny little particles that are floating around in it, and it never settles out, which is why it's not clear. Okay, if those particles settled out, it would be, your milk would be clear, and that would just be strange. And we also have brownie in motion. which talks about the random movement in a colloid. So basically, the particles, they're in their solution, right? And as they're moving in completely different directions, okay, you occasionally have times where they're going to run into each other. And when they run into each other, they just bounce off. Okay, well, and they keep doing that and they keep bouncing so much that they never end up falling to the ground. The force just kind of sends them everywhere. And the Tyndall effect, it describes the scattering of light in a colloid. So you can see here how the light just seems to go straight through this yellow solution, but here it gets wider. It kind of goes out. It's being scattered. This is why you don't drive with your high beams on when it's foggy outside, okay, because the light will just scatter on the fog instead of actually breaking through it like you want. Now, a homogeneous mixture is two or more substances that are physically combined, but the difference is that they're uniform throughout, or it looks the same, okay? Now, a solution and a homogeneous mixture are the exact same thing. So somewhere on your notes, you need to write homogeneous equals solution. They are the exact same thing. Okay. Now, a solution or a homogeneous mixture is composed of two different substances, a solute and a solvent. Now, the solute is the substance being dissolved, and the solvent is the substance that's doing the dissolving, the larger amount. So, for example, in Kool-Aid, the solute would be sugar, okay, in the little packet, and the solvent would be the water, okay. So we're going to get some more practice with that, okay, because there are many types, okay. You can have a solution that's completely made of gases. For example, air. Nitrogen makes up a majority of the air we breathe, and oxygen is dissolved in it or mixed into it. Not really dissolved, but yeah, more mixed into the nitrogen, but it's considered the solute. You can have things that incorporate liquids. Pardon my yawn. Okay, a little sleepy while I'm making this video. The carbon dioxide here can be dissolved into liquid water, and that's how we get sodas. Yay for all fizzy drinks, carbonated water, things like that. If you want to make Kool-Aid, like we talked about before, the sugar is dissolved inside the water. And vinegar, you have acetic acid, which is a liquid dissolved in another liquid or mixed into another liquid. And since they're both clear, I've got a clear liquid here, clear liquid here, you really can't tell the difference. Now, a solid solution has a special name called an alloy, okay, and that's very important to remember. And an example would be steel. Steel is made up of iron and carbon, and the reason why is because iron on it by itself is strong, but not nearly as strong as when you mix it with a little bit of carbon, and it really combines in order to increase the strength. So, solubility and miscibility. Okay, if you're filling in your guided notes, this has a lot, so you might need to pause the video. But soluble means able to be dissolved. Okay, so for example, sugar is soluble in water. Okay, and this word soluble, that's a key vocab word. Insoluble means unable to be dissolved. Okay, so sand is insoluble in water, which is why we have beaches, right? If sand was soluble or dissolved in water, we would not have beaches to go on vacation and like lay on and get tan and things. Now, miscible means two liquids that dissolve or mix with each other. Okay, so food coloring is miscible in water. And that's a third really important vocabulary word there. Immiscible means that two liquids are unable to dissolve or mix with each other. So oil is immiscible in water. So if you look at this picture over here, you can see the oil from the tanker truck or the tanker ship, okay, that's been leaking, okay, and when fish go through that, okay, there's no oxygen because water and oil do not mix. And so instead of their gills breathing in water that has oxygen for them, they breathe in that oil and it causes them to die, which is why there's so many problems with oil spills in the ecosystem. But it also allows us to help clean it up a little bit easier because there's this clear boundary on the edge. I can almost draw a line exactly where, it's um, breaking up and where it is. And so that helps scientists really be able to narrow it down and clean it up. And solubility refers to the amount of solute that will dissolve in a solvent. And it's dependent on temperature and pressure. And so it's about the amount, not will it dissolve, but how much. Um, and different factors will affect that solubility. So one is going to be temperature, okay? Now this is important. Solids, when you increase the temperature of the water, you increase the solubility or you increase the amount that will dissolve. Okay, that's terrible handwriting. I should probably rewrite that. But it increases the amount, okay? And so that means they have a direct relationship with each other. When you increase temperature, you increase solubility. Now, gases is the opposite. When you increase the temperature, you decrease the solubility. They won't stay dissolved, okay? So this would be an indirect relationship, okay? Now, if we look at these two examples, like this coffee cup here, the hotter your coffee is, the more sugar you can dissolve. But with this pond, okay, the hotter it gets, okay, the less oxygen that will be dissolved in the water because the oxygen will just evaporate and leave into the atmosphere, and that leaves a lot of dead fish. Now, pressure, which is our second factor here, it will have no effect on solids. But with gases, it will increase my solubility. Okay, so for example, carbonated drinks, I know it got cut off there, but if you have a carbonated beverage, when you open it, it goes psh, okay, and that's because the pressure is being released. Everyone knows once you open the Coke, that's when it starts to go flat, and because that pressure was keeping your carbon dioxide in your soda, and now it's no longer there. Now, rates of solution. Okay, so temperature and pressure affect how much can dissolve in there. Rates of solution talk about how fast a solute will dissolve, not how much. So heating, okay? When you heat something, you increase the kinetic energy or the speed of the atoms. Okay? Now, this serves because when you're increasing the speed of the atoms, you're increasing how fast they're moving, how often they're colliding, and so you're increasing the rate at which they will dissolve. And agitation will do the exact same thing. They're going to increase the speed of the atoms. You're literally pushing them around. Now, crushing, what it does that makes it so special is it increases the surface area. Okay. Now, the smaller the pieces you have, the faster it will dissolve. Okay. Now, carbonated drinks. We really want to talk about this because this is a perfect example of how these different ideas come into place. Because the steps in order to make a carbonated drink have to happen in this order, otherwise it won't work. So, what we have to do is we have to heat the solution to dissolve the sugar. And then in step 2, you cool it down to dissolve the carbon dioxide in the drink to carbonate it. Okay. And then in step 3, you put the can under high pressure to keep the gas dissolved. Because we know that our can is not always going to stay at this cooled down temperature. Okay. And so the reason why these two, step 1 and step 2 are not flipped is because if I cooled it down to put the carbonation in and then I heated the solution to dissolve the sugar, all the carbonation would leave. Okay, it has to go in that order so that they don't countermand each other. Now, colligative properties. Okay, colligative properties are properties of a solution that depend only on the number of particles. Oh, that's key there. It's only on the number of particles dissolved in the solution, not on the type. Okay. So for example, there are two types of colligative properties that we really talk about and see in real life. One is freezing point depression, and that's when your freezing point is lowered when the substance is dissolved. So that's why we put salt on roads so that they don't ice over. So we know that water freezes at 32 degrees Fahrenheit or 0 degrees Celsius, right? Well, when we add salt to it, what happens is the freezing point lowers. So now instead of being 32 degrees Fahrenheit, it now has to be 30 degrees Fahrenheit, depending on how much salt you add. Okay. Now this is really important because if our temperature only gets to 31, then even though it should have frozen, the roads should have frozen, it won't because of its lowered freezing point. Okay. Um, Now, what I mean by number instead of type is if we have NaCl, which is table salt, okay, so this is table salt, and I have magnesium chloride, which is Epsom salt, okay, it's what you use in your bathroom to take a bath when you're really sore, helps relax your muscles. Now, sodium chloride has two particles. It's got sodium and chlorine. So two particles. Whereas magnesium has one magnesium and two chlorines. So it's three. So when we think about which one would be more effective, magnesium chloride would be the most effective. Okay, so if you're planning on dumping salt on your porch to make sure your steps don't freeze, you would want to use the Epsom salt instead of the salt you put on your French fries. Now, boiling point elevation is kind of the same concept, except our boiling point is increased, meaning it has to be hotter in order for the water to boil. And this is really important for antifreeze in our car. So antifreeze keeps your engine from overheating during the summer, and it keeps it from freezing during the winter. And this allows us to not have some very costly repairs in our car.